Good morning, all of you. Today we are here to discuss the topic that is Introduction to Semiconductor Devices, which is considered as the most important topic in the electronic devices. So, starting with this introduction of semiconductor devices, first of all, the basic what are these electronic devices? So, electronic devices are those that control the flow of electric current for the purpose of information processing and for the system control. Basically, they are classified as active devices and passive devices. So, first of all, as we discuss, what according to the nature we classify them as active and passive devices. So, what are active devices? Active devices are basically they are acting as a transmitter. That means they are providing energy to a particular circuit. So, their role is particularly is of transmitter. Second, the passive devices are those which are acting as a receiver. That means they are taking energy from a particular circuit and their role is particularly in the passive mode. So, the basic examples of active devices are BJT, IC, MOSFET. These are the examples of active devices. Passive devices are resistors, capacitor and inductor. Now, based on the second classification of electronic devices, based on the electrical conductivity, how we classify our devices. So, based on this property, they are classified as conductors, semiconductors and insulators. So, what are the conductors? Conductors are those which have very high conductivity and the energy band gap in case of conductors is almost zero. What are semiconductors? Semiconductors are those devices whose properties are lying basically in between the conductors and insulators. So, what do you mean by these properties? Properties like resistivity, conductivity, energy band gap. These are the basic properties which lie between the conductors and that of insulators. So, their conductivity is in between the insulators and the conductors and the energy band gap is at most around 1.1 electron volt for the silicon and 0.7 electron volt for the germanium. Next and the last is the insulators. Insulators are those in which the conductivity is extremely low. The energy band gap is almost at most we can say that is greater than 6 electron volt. And the examples in case of insulators are rubber, wood, plastic. These are the basic examples of insulators. As I discussed in earlier slide also, conductors, they have very high conductivity. They provide ease in the flow of the charge carriers. The energy gap is zero and the basic example in this category are gold and copper. Semiconductors, their conductivity is in between the conductors and insulators. The energy band gap is 1.2 electron volt and the basic examples are silicon and germanium. Insulators, their conductivity is extremely low. The energy band gap is more than 6 electron volt and the examples are glass and rubber. So, based on the electrical conductivity, we are classifying our devices as conductors, semiconductors and finally as insulators. This is the band structures in case of insulators, semiconductors and insulators and metals, and what we are observing in this, the energy band gap in case of conductors, that is in case of metals, it is almost zero. In case of semiconductors, it is comparatively small as compared to the insulators and it at most at the value of 1.2 electron volt. Finally, for the insulators, it is around more than 6 electron volts. So, this is the band structure or we can say the energy band diagram for the three categories of the electronic devices which are metals, semiconductors and finally the insulators. Now, what is the basic need of these semiconductor devices? First, they are easily available. Second, they are very much cost effective. And second, and the last is the conductivity can be controlled or it can be modulated as per our requirement. Now, coming on to the classification or types of semiconductor devices. They are basically classified into two categories. The first one is the intrinsic semiconductors. The second one is the extrinsic semiconductors. Extrinsic semiconductors are further classified into two categories, which are of N-type semiconductors, and the next is P-type semiconductors. The N-type semiconductors are formed by adding the pentavalent impurities such as arsenic and antimony, and P-type semiconductors are formed by adding trivalent impurities, which are boron and aluminium. Now, what are the applications of these semiconductor devices? They are widely used in diodes, in transistors, and in integrated circuits. Now, moving on to the next part, which is the most important, or we can say that important part of Unit 1, is types of solids, or what are solids. So, crystalline solids are arranged in a fixed geometric pattern or lattices. So, before defining these solids or types of solids, these are the terms that are required for the basic understanding of the types of solids, which are lattice, unit cell, and third is the basis. Now, what is lattice? Lattice is a three-dimensional, infinitely repeating arrangement of points in a space that represent the position of constituent particles. That means it is a three-dimensional structure which is formed by repeating a particular unit, that is forming a crystalline structure, or we can say that a space of 3D structures. Second is the unit cell. Unit cell is the smallest repeating unit in the crystal lattice, and which is actually a two-dimensional structure. Basis is the atom or group of atoms that are associated with the each lattice points within that unit cell. So, if we consider these three terms are entirely different from each other, lattice is completely different from the unit cell, and unit cell is completely different from the basis. These are the diagrams depicting the crystal lattice and unit cell, and which gives the better visualization in differentiating between the unit cell and the crystal lattice. And what we are seeing in this structure is that unit cell is the smallest unit which is used for making this crystalline structure, and unit cell is particularly three-dimensional or two-dimensional, but it is the smallest unit or the smallest unit used in the repeating structure. This is the crystalline structures which is formed by the combination of these multiple unit cells. Now, coming on to the types of solids, first one are the crystalline solids, next is the amorphous solids, and the last is the polycrystalline solids. So, as we can see that in case of crystalline solids, they have a regular arrangement, or we can say that the periodic arrangement of atoms in a particular structure. In amorphous solids, what we are saying is that they have a random or non-periodic structure. The atoms are arranged randomly, not in a particular fashion, but they are arranged in a non-periodic fashion. These are the diagrams depicting the three solids which are amorphous, polycrystalline, and crystalline. And what we are observing from this diagram is that in case of crystalline, the atoms are arranged in a particular fashion or in a particular periodic manner. That means they are following some pattern if we are designing a crystalline solid. Next are the amorphous solids, in which we are observing is that the atoms are randomly arranged and they are not following any pattern. That means they are arranged in a non-periodic fashion. The third is the polycrystalline solid, in which the entire solid is divided into small grains, as we are seeing the different ROC, that is region of interest, and these region of interest ROIs are called grains. And what we are observing in these grains or in these ROIs, the atoms are following a particular pattern. That is, in case of polycrystalline, the atoms are showing the particular or periodic fashion in a particular region of interest. That is, in grain, they are showing the periodic fashion, but if we consider the entire structure, it can be considered as that it is in non-periodic fashion. These are the lattices, types of lattices, in which the first category is of simple cubic. The second is the face centered, in which we have shown the basic structure, the atomic packing factor, the calculation of the atomic packing factor. Similarly, for the face centered cubic lattice, we have shown the contribution of atoms. What we are observing in this simple cubic lattice structure is that in simple cubic, the atoms are arranged at the 8 corners of the cubes. So, accordingly, the arrangement can be calculated and atomic packing factor is calculated using that concept only. In face centered, what we are observing is that we have 8 atoms at the 8 corners and plus we have 6 atoms at the 6 faces of the cube. What we have obtained after calculating atomic packing factor, in case of simple cubic, it comes out to be around 50%. In case of face center, it is 74%. The last one is the base, that is BCC. In BCC, we have 8 atoms that are arranged at the corners, and there is one atom whose contribution is particularly at the body diagonal of that cube. So, in this case, the atomic packing factor is almost 68%. So, these are all about the calculative part for the crystal lattices structure, in which we are classifying them as simple cubic, base centered, body centered cubic lattice, and last is the face centered. Now, moving on to the next topic is that what are the EK diagrams? Basically, why we are using, what is the concept of EK diagrams in electronic devices or in semiconductor devices? What are their significance? So, before coming on to the significance, it is very necessary to know what is a EK diagram. So, EK diagram, it represents the relationship between the energy and the momentum of a electron in a material. It displays the allowed energy bands, that is your conduction band and the valence band, and the band gaps within the material. The curvature of the EK curve in conduction band and the valence band represent the effective mass of an electron and the holes. Now, what is a effective mass? Effective mass is basically the mass of an electron when it is interacting with all the particles. That is, it is not in a rest condition. This is the diagram of EK diagram, in which is basically representing a continuous curve, and the atoms are so much closely spaced that it is depicting a continuous curve, and this is the bottom of the conduction band, this is the top or the maximum of the valence band, and this difference between the edge of this EC and EV gives you the energy band gap, which is EG. And these are the electrons which are located at the minima of the conduction band, and the holes which are at the maxima, which are located at the maxima of your valence band. This is all about the EK diagram. This is also one of the pictorial representation of EK diagram, in which we are observing is that whenever the electrons particularly combine with the holes, that is the electrons at the minima of the conduction band edge combine with the holes at the maxima of the valence band, then the energy is released, particularly in the form of light, as we are observing. So, this is all about this the diagram of EK diagram. So, coming on to the significance, why we are using this EK diagram, or the major application of this is that we use this EK diagram to differentiate between the direct and indirect semiconductors. This EK diagram plays a major role in this differentiation, that it helps in determining which is a direct band semiconductor or which is indirect band gap semiconductors. Particularly in this EK diagram, this particularly your x-axis is representing your wave vector or momentum, and your y-axis is representing the energy of an electron. So, that is the term, that is EK diagram, and its significance is it helps in differentiating your between direct and indirect semiconductors. So, summarizing all the things what I have covered in this entire lecture is that First of all, I have covered the basic introduction of your semiconductor devices. Their classification, the first classification is based on their nature of device, that is your active and passive device. The second classification is based on the electrical conductivity, which is in which we classify our devices as conductors, semiconductors and insulators. Next, after that we have, I think, we have covered the classification. After that, the band structure, in which we have depicted their classification according to their band gap. Then finally, the need, why we need these semiconductor devices, and what is the major need nowadays of using all the semiconductor devices in all the major applications. Then types of semiconductor devices, their applications. The next part, which is considered as a part of your first unit, particularly dedicated to the students of second year, is that of solids. Solids, we have gone through the crystalline solid, amorphous, polyamorphous, and particularly their crystal structures, their atom contribution. And the third part that we have covered in this lecture is your EK diagram, which is also the most important part of your first unit of electronic devices. Thank you. This is all about that I have to discuss in this lecture.